So last time we left off, we were starting out with some conservation of linear momentum, and I stopped just before we got to collisions. We've seen how the total momentum of a system is conserved throughout any type of interaction. In a lot of my examples were of someone either catching something and both of the things moving, or maybe someone on like a frictionless surface, or imagine an astronaut out in space, like throwing something. These two objects have a combined momentum that they share. And so this total momentum of this sphere I'm drawing around this system, this total momentum is conserved. Now we get to collisions where that same sort of principle happens. This is sort of the meat of this chapter. There we go. Collisions. So we can examine a collision using linear conservation of linear momentum. For right now, we're going to, let me bring up this and that. Okay. For now, we're going to ignore the actual moment that something is colliding with another object. So a car crash at split second where the two cars are changing velocities very quickly, or a bouncy ball hitting a table or the ground, that split second where it changes direction. We're ignoring that exact moment just for right now. I'm going to do that in probably like 5 minutes. We'll sort of examine that. If we take sort of two snapshots of a collision, there is only before a collision and then after the collision. The total momentum before, that's the total momentum before a collision and the total momentum after. We're going to compare those two things, and they should be equal due to the conservation of linear momentum. Momentum is always conserved, so it's going to be the same no matter what. There's two types of collisions. There is an elastic collision and inelastic collision. Elastic and inelastic. Sometimes you might hear the phrase perfectly elastic, perfectly inelastic. This is just the question trying to be very specific on what is happening. So a lot of times in the real world, things, bounce a little bit, things stick together a little bit. Let's get into what these are meaning. So elastic collisions, we're looking at the ones for this one. I'm going to say momentum is conserved. And this is a type of collision where something will bounce off of another thing. This is easily thought of as an elastic ball, a bouncy ball. Drop it from some height. It will nearly bounce off the ground and nearly come back up to the same exact height if there was no air friction or any sort of loss of energy through the environment, that bouncy ball, this system, would continuously go forever. So for this elastic collision, things bouncing off of one another, I'm going to say kinetic energy is also conserved. Is conserved, yeah. Things may hit one another, change directions, and they may give some of their own velocity to another object. We can do some calculations with kinetic energy this way. Basically, I should have put this point first. Objects bounce off of one another. Objects bounce off one another. Okay. This is the case where objects bounce. Inelastic is the case where objects stick. Let me put that point first. So objects stick together. Think of stick together. All right. Think of if I were to drop a ball of clay from the same height I dropped the bouncy ball from, it would hit the ground and it would splat, and it wouldn't bounce at all. It would sort of stop moving. Or some sort of collision where the two objects maybe mesh together or combine. This is an inelastic collision. Perfectly inelastic and perfectly elastic. So the sort of thing that I have in the parentheses right here, that's just sort of clarifying that momentum is conserved for this. Actually, momentum is conserved for both of them. Let me finish writing my points before I. So for this one, momentum is also conserved. However, kinetic energy is not conserved for an inelastic collision. Now, from conservation of energy, we've learned before, we know that this energy isn't just disappearing somewhere, it's going into the surroundings. If I drop a ball of clay and I say kinetic energy is not conserved, what I'm saying is that the energy that it took for this ball of clay, I'm holding up at a height, I drop it, it transforms into kinetic energy, and it splats on the ground. And through sound energy, through thermal energy, the energy is sort of dissipating. This is what I mean by kinetic energy, or specifically kinetic energy is not conserved. Then when I'm saying a perfect system, just saying, think of the most basic of these two examples, bouncy ball, a lump of clay. Let's look at sort of what the structure of the equations would look like. There's about, I want to say like 7 or 8 examples of elastic and inelastic collisions in your book. All of them are going to kind of start like this. You're going to look at a situation before the collision, which for a elastic collision, you're just going to add up the total momentum of the system. So however many objects you have, however they are moving. So the mass of one object times its velocity. So this the momentum of the first object plus a second object. And so this is before. We're going to compare that to the total momentum after. So I'm just going to say mass 1 v1 prime. So however that first object changed velocity, that's what I'm meaning by prime. And second object, second velocity prime. So however it's changing in any sort of problem that you're given. That's sort of the starting point. I can also look at kinetic energies too. So kinetic energy, the first object, is kinetic energy of the second object is equal to, however that's, remember what kinetic energy is made of, it's 1/2 mass times velocity squared. So velocity is going to maybe change. You're going to have to factor that into this kinetic energy. So I'm just going to say kinetic energy 1 prime, kinetic energy 2 prime. This is how you can sort of approach, I'll say 90% of collision problems. Just setting up the momentum that you know, total momentum before, total momentum after. And we can do this arrangement right here for an elastic collision because kinetic energy is conserved. For an inelastic collision, these two objects are going to stick together. So in the before scenario, let me arrange it. Before, these two objects are separate. They have their own independent motion, velocity, wherever they're going. But after a collision, they are sticking together. So they're stuck together. I can say m1 plus m2 is another velocity, but we'll say that's, we'll keep them separate for now. m1 is now moving at some different velocity that's unknown, or maybe it's known. The problem you're given. 2 is v3. And you see I can factor out the v3, and this is how you see the two masses are sort of combined, moving at this new momentum. Do the same sort of thing for kinetic energy, but I have to be careful when doing something with in an inelastic collision, because it's moving at a new velocity after a collision. So typically the question won't ask about kinetic energy for an inelastic collision. There is a specific equation for kinetic energy for inelastic collisions. It's in your book. I don't think I'll be getting to that. It's a bit too detailed for right now. Let's go over there we go. Let's go over that sort of split second where an object is changing direction or two objects come into contact with one another. All right. think about that's. I'm gonna shrink all of this just a little bit. Think about you like want to chop some wood, or you have a board that you're trying to hit or snap in half. You can gently push on it, start pushing harder and harder, but there is sort of gradual limits that you can reach, and it takes a lot of effort to get to the force required to maybe snap this board in half. Sometimes it would be easier just to hit it and it will snap in half very easily. But this is a type of collision. You are bringing one object onto another, and there's this large force delivered in a very split second amount of time. This is what is known as an impulsive force. Within a very short amount of time, there's this large force delivered. One object is, uh, you know, a baseball thrown at a baseball player is hit with a bat, and there's only a split second where the ball is in contact with the bat, but there is a large force delivered between the two, causing the baseball to fly several hundred feet in opposite direction. So we want to look at this impulsive force. It'd be valuable to know how much force is being delivered at the point of impact. You can do some sort of analysis on if a material is strong enough to withstand something that's being hit or changing direction suddenly, applying a very sharp force. So we have this impulsive force. I don't quite like how they have the symbol for impulsive force is I. So later on, we're going to get to angular momentum and moment of inertia, and it's also labeled as I. So right now, if you see this, be careful of what it's asking. So the impulsive force is just a large force over a small window of time. So some very large force over a small window of time. Large force over a small sliver of time, or within a small amount of time. And we've seen from the previous class on momentum that a force can be described as momentum. A force was a change in momentum over time. So I'm going to rewrite this integral. So where we know this integral, before we had it as something like this. We saw this was just the change of momentum over a small sliver of time. Which ultimately turns out to be just a difference of momentums. So this means that the impulsive force is just the change in momentum of one object. This can be a baseball hitting a baseball bat. The baseball will have its own mass, change of velocity very quickly, going from positive to negative. Rearranging this equation, we can determine the average force and the impulse again from this average force. Say we didn't want to do this integral all the time. We just say the average force is just a difference of time. It's the impulsive force, average force. And finally, it's kind of cyclical. We could say the impulsive force is just the average force times the amount of time an object is being amount of time it takes for this collision to start and stop. Impulse from average force. Okay, so from this, you could just take away that the impulsive force is just a large split-second force applied between two objects that are in a collision. Okay. From here, we have an example of an impulsive force. Okay, so you try to chop some firewood with an axe, but the axe keeps getting stuck in the piece that you're working on. The axe has a mass of 1.5 kilograms and is moving with a velocity of about 3 meters per second. As it strikes the wood, it gets stuck just about 10 centimeters down into the piece of wood. Beyond this point of contact, so beyond that initial surface, we want to know is what is the impulse that the wood is applying on the axe? Also, what is the approximate collision time and the average force exerted on the axe? So let's believe we have everything we need to start out. The impulse is just the change in momentum of this axe. Let me, before I change in momentum of the axe, which is mass times change in velocity. And let me define sort of a direction that I'm calling for this problem. We have an axe we're looking sort of head on, and it's a piece of wood. You have an axe that is moving downward, hitting a piece of wood, and travels down about 10 centimeters and gets stuck. Its initial velocity, since it's traveling down, I'm just going to call that negative 3.0 meters per second. And its final velocity, 0, since it's getting stuck, or it's stopping completely within this very short period of time. And this piece of wood is applying a force on the axe. All right, now we have sort of a coordinate system. Let's get started. Mass of the axe is 1.5. Final velocity minus initial velocity. So we have an impulse of 4.5. This is kilograms times meters per second. That's not quite a Newton. So that actually it's positive. 4.5 kilograms per meters per second. In the, yeah, let's add the direction also. So this is J hat. So it's going down. So I'm sort of clarifying the J hat direction. Not quite a Newton, but let's make it 4.5 newtons over seconds. So I'm just sort of making it into this form. So that'll help us out in a little bit. Next up, what is the approximate collision time and average force exerted on the axe? So from the kinematic equations, we know that the change in displacement, the displacement of an object is equal to velocity time, or I guess average velocity times time. And we've only given 2 velocities. That's good. To do an average, we have 1/2 the initial, the final is a change of time, and we want to find out what this time, how long it took for this axe to stop. So let's solve for delta t in this equation above. 2 delta y that is just following through. We have, oh yeah, so it's going from the top of the wood right here, it's going down. So we're going to call that a negative 10 centimeters or 0.1 meters. And we have these 2 velocities that we know. We get Let's just go straight to the result. .0.067 seconds for the axe to come to a stop. Now we have an impulse, we have a time. We could find the average force applied to the axe. It's just 4.5 newtons per second, and this is in the j hat direction, over 0.067 seconds. You can see kind of why I left, or why I made this into newtons here at the top. We have a force of, or an average force, about 67.2 newtons in the j hat direction. So that's the force being applied on the wood. And the wood is applying on the axe. That's Newton's third law. So this meaning is that within this brief amount of time, this axe is having this force applied to it in order to stop it. It's a very large force compared to, this is an additional way to find forces if we weren't given a time already, in order to use other kinematic equations. Okay. So we don't see impulse too often. I may have one problem or so on the homework, but this is at least good to know if you're going into any sort of, or I guess that'll be for the next example. If you're going into any sort of field where you have to examine collisions of anything, you'll definitely see this pop up. Okay. The next example is, I think, good just in general for getting used to two-dimensional collisions. Okay. We have, all right, so there we go. A 1,500 kilogram asteroid is traveling to the right at an unknown speed. A 3,000 kilogram satellite is traveling directly up at a speed of 80 kilometers per hour. These two objects collide and stick together in a perfect inelastic collision. The two then move together in a new direction, 50 degrees above horizontal, at some unknown velocity. So what we're wanting to figure out is how fast the asteroid was before the collision. Let's draw a little picture of what's happening. You have an asteroid, sort of this ball. It's moving perfectly to the right. It has a mass, it has a velocity. We're just going to call it, this first object, M1 and V1. And we have a satellite. Just going to make it a square. It's moving directly up. has its own mass and its own velocity. These should be vectors. There we go. This is the before scenario. So I'm going to label that even above my picture. They happen to collide and then move at a new sort of trajectory. Let me draw the after scenario. I'm not going to add it here because that'll probably mess up or make this picture a little cluttered. What I'm going to do is combine these two sort of right here, like that. And now they're moving at some trajectory like that. They're stuck together, perfect. M1, M2, a perfect. There we go. I need to do that so I can do the coordinate system. Since we know this is going to be a two-dimensional problem, let's break this up into its own coordinates. So we're going to say this is V3, some new unknown velocity. That is an angle above horizontal. This is a vector. Vectors are made of their own individual components. So I'm going to say this is V3x. And there we go. We'll go like this. There we go. V3y. So it's made of its own components, like that. Yeah. Like that. And I'll say this is the after the collision. So the exact moment of collision is important to us. What we want to do is compare before to after. So M1, V1, M2, V2 is equal to M1 plus M2 times this new unknown velocity, V3. We can't necessarily jump into this problem just like this as it is, because they're moving in orthogonal directions. We need to break it into its individual components first. So let's look at just the x component, or just the horizontal components. So we have the horizontal components. Well, it's all being provided by that first mass, the asteroid. And nothing from the satellite. And then afterward, there is this little components that they both share. Okay. What is V3x though? This is maybe something we don't have, but we could at least express it in a term that we know already. Let's rewrite this as 1 plus M2. This is V3 times cosine theta. We are given an angle of this new trajectory. Here we go. Let's do the same exact thing for the y component, or the vertical components. So there's nothing from that asteroid. And all of it's being provided from the satellites. All of these V's, they should have a vector sign on top of them. Or I guess not this. No, this one. This one's good. This one is also good. Okay. Or no, I'm sorry. Because I have this as just X components, that's why I don't need vector sign. Okay. Same thing, M1 plus M2. V3Y. We could be more specific. That's just the magnitude of that velocity times sine of theta. It's way too big. I have to shrink it minutes. So let's solve for one of these V3 values. And then insert it into the other equation. So let's solve for this one right here. We'll say that's M1, V1. I'm just rewriting this equation that we have right here. That is M1 plus M2 cosine theta, solving for V3. All right. Now that we have this, let's place this new V3 that we found into the other equation right here. Let's shrink this. Okay. So we have M2. Zoom in just a bit. M2, V2. M1 plus 2. And then instead of V3, I'm going to insert this new form. All right, and from here we can see that these masses cancel out. We're left with something that looks like this. V2, M1, V1. Sine of theta over cosine of theta. We know what sine over cosine is already. That is just tangent. It's going to go like this. Tangent of theta. So we have M2, V2 over M1, V1. And we're doing all of this just to solve for V1. We're going to get V1 equals something with terms that we know. Oops, sorry. So that's m2v2 over m1 times tangent of theta. And in this expression, we have all of the terms that we know. So that's the mass of the satellite, the speed of the satellites, it's in kilometers per hour. We have the mass of the asteroid and just the angle that the end product is making. Let's put at the very bottom, V1 equals 134 kilometers per hour. And I should put I have right there. Since it is completely horizontal. But you see, that is how in a typical problem, we weren't given this unknown third combination velocity. Well, that isn't quite important to us when we can just use it down here. See, we've used it to solve for something that we're interested in. Okay. That is a good example of an inelastic collision. I think if I was going to do a simple elastic collision, it would just be like one or two lines. So I'll leave you, just to see an example of a elastic collision on the homework. There's several in the book also. Okay. Now that we're done with that, later on in this chapter, there is, what was there? There was like variable mass. Let's see. There was center of mass and continuously varying mass. So this is something for like a rocket that is being propelled through space, or just to get a rocket off of Earth's surface, there needs to be a large proportion of fuel accounted for. But that fuel itself has mass. Having more mass means that you need to launch the rocket faster. In order to get it faster, though, you need more fuel. So there's this sort of feedback loop of needing a specific amount of fuel versus the amount required to actually go anywhere. There is what's known as the rocket equation. You guys can look up. It's a bit too specific for anything I am going to go over. It's also related to continuously varying mass and rocket propulsion. Yeah. So if an object is moving with some velocity and it's losing mass, that means it's losing momentum as it travels. Typically, we only are going to be seeing the velocity change because an asteroid moving through space, an asteroid doesn't suddenly dissolve and become less as it moves through space. So typically we'll see just the velocity is the one changing. And so I'm going to leave out the varying mass section. It is interesting, but it is a bit too specific. With that, we're basically done with chapter 8, the conservation of linear momentum. As things move, you just define your system, define what's in the system. So the system consists of this asteroid, this satellite. Just going to look at this bubble. You say the total momentum in this bubble is going to stay constant in whatever happens. It's a very useful tool. Moving on to the next section or the next chapter, we have rotation. Let me pull up rotation. Rotation. So for all of our calculations, our work we've done up to this point in the semester, we've used a standard coordinate system, sort of X and Y. I could have been adding a third coordinate for some sort of depth, but for this class, it's easy to make problems that you write as two-dimensional. For something that's spinning, we've done a very few amount of things that have been spinning so far. That's because it's very awful to try to deal with something spinning with a standard Cartesian coordinate system. Let me explain. So we have this object, this wheel we're trying to spin. And we want to know its position. Like say we have a bike tire and we mark a dot on the edge of it. Here's a bike tire, and we've lined up the center, the axle, with the center of the coordinate system. That makes it so much easier, but it's still a very difficult problem. So say we want to find the we just mark a dot somewhere on the edge of this wheel. Okay, where is that dot on this coordinate system? You'd say, okay, well, I have to find its displacement vector. This is two-dimensional. So I need to find that. I need to find R. In order to find R, I need to know its exact coordinates. What is R made out of? X and Y. You doing this, finding the magnitude. Easy, no problem. Okay, now you spun it just a little bit and the dot is now here. You sigh, and now you have to do it all over again for something that is just moved over slightly. It's a completely new displacement vector, R. So I'm going to say that's R1. You see, I could do hundreds, thousands of these as it travels around. Let's just, for example, I let it spin for a bit. I'd have to find a completely new one, completely new displacement vector for it as it gets over here. This is a nightmare to do in Cartesian coordinates, or as store standard X, Y, Z coordinates. It's not just X, it's negative X. There we go. Let me just clarify. We have to recalculate. Recalculate for every new position. On the spinning object. New position on this spinning object. This is the easy example. This thing is a wheel that is always the same dimension on each side. What if I wanted to know, some obscure shape that was spinning? I don't even want to get started. Let's go into how we can make this easier. We need to define a system that spins. So we are already sort of in the mindset of this thing is spinning. I don't want to have to worry about X and Y. I just want to know, how is this thing spinning? That leads us to sort of defining rotational kinematics. So just how things, so it's us describing how things may rotate. We could do our own new system to measure distance, velocity, acceleration within this rotating, spinning reference frame. In this example I just did up here, that was just with the position. Let me add on top of that velocity. So we have this first point up here. It's momentarily having a velocity pointing that way. And for this second position over here, it has a velocity going that way. It's a nightmare. Okay. Moving on to rotational kinematics, we can define the displacement of something that's spinning. Some distance, some point on a rotating surface. And this is sort of general enough that it doesn't have to be a perfect circle that's spinning. We just need to know what is the distance from the point that this object is spinning. We bring up the same exact picture. We zoom out a bit. Like that. Okay. Guess I have to go like that. Okay. So we have the angular displacement. That is just a sort of sliver of how this thing is changing, sort of an arc length. So let me do this. Let me write it out first. I. This is the radius times the angle moving through. Okay, let's do that same exact type of path that I did up here with point 1 and point 2. Point 1, somewhere right there. Point 2, somewhere right there. Since this is the same exact point, I just need to know the radius. How far away from the axis of rotation is this thing? Is this single point spinning? So as long as I know the radius, I know it's going to be that far away right here. It's going to be the same exact radius away over here. That makes it a lot easier already. So what this equation is saying right here is that we want to know angular displacement is how far along this curved path did this object move. So that curved path is this right here. So that's S sub I. I'm just going to call it S. So that'd be this arc length is the radius of this circle times how far or what kind of angle, theta. Try to make it look, there we go, theta. The angle that this point swept through. So I'll go like this, arc length. Radius, angle moving through. In radians, yeah. So we need to be careful because since we're switching to this system where everything is rotating, everything is related to a circular path, we're going to switch to radians. You might see this is ds and d theta. What I'm saying with this, let me sort of recreate that picture right next to it. I'm just saying a small sliver of an arc length is equal to a small sliver of displacement, or a small sliver of, change in angle. So it'd be like R, R would be a small sliver of an angle. It would be a small arc length. And it's just adding up all of these tiny little slices of this pie as it makes its way from one point to another. Since we are transferring to radians, a system up with radians, we need to know that if we do have a change of angle, it's just the whatever the, we'll just say S over R. Whatever the arc length is divided by the radius. In radians, we have the arc length of a complete trip around a circle. Say for one complete path around a circle, so if we start at this point, one complete path all the way around, we've traveled a distance of 2 pi times the radius. So we have 2 pi radians. And that is equal to 360 degrees. Basically, that's just one revolution. I'll just put over here also for people later. adding up the small slices of displacement. Okay. I don't know why that dot's so much bigger now. Okay. Now that we got this way of measuring a displacement on a circular path, let's find the angular velocity also. Angular velocity is simply just the change of the angle that you're having over some amount of time. So I go from one point on a arc to another point. It had a change of angle. So angular velocity, that is just this. This is it's not quite a W. It's a Greek letter, lowercase omega. Yeah. I'll probably just be writing that as a lowercase w in a lot of my writing. So that's just the change of angle, the small sliver of angle for a small sliver of time. So if we add up all of those small slivers together, we get this large change of angle. Say we go from here to here. That will be some velocity that it's moving along this circular path. And that's all from this change of angle. It went from 0 all the way to this new angle. By the way, on a radian coordinate system, we have 0 right here. Up at the top, we have pi over 2. Over here on the left, that is pi. The bottom, 3 pi over 2. One complete revolution is, if I go all the way around, then it's 2 pi. Okay. And I should add also counterclockwise is positive. Previously, we had a system of things moving to the right were positive, things moving to the left were negative. In this system, things that move counterclockwise are positive. Since there is this positive change of angle, it's increasing. Okay, we have angular velocity. We could also find the angular acceleration. That's just the change in velocity. Angular acceleration is labeled with an alpha. So that's this symbol alpha. Looks like a goldfish. Alpha, let's say the average acceleration, average angular acceleration, that's just a change in angular velocity over the change in time. I write it in the say multiple, add up multiple small slivers, w dt, and that's just second derivative of its change in position. You see there's a sort of a one-to-one relationship between the Cartesian coordinates, sort of way we were dealing with things. So position, the derivative of position is velocity. The derivative of velocity is acceleration. It's the same sort of one-to-one relationship to things that spin. The only thing that's changing is the symbols that we're adding to this. That's just to clarify that we're talking about something that's spinning. Now, given a constant angular acceleration, something's has a constant angular acceleration, so it's constantly getting faster and faster as it spins. We have the rotational kinematic equations. It doesn't have to, let me back up. It doesn't always have to be getting faster and faster. It could have a constant angular acceleration of 0. That also counts. But in this case, and from what I've said before, it's the same exact form as the linear kinematic equations. Only thing that's different is the symbols we're using. That's to clarify that we are talking about something that is spinning. So this is the equation for velocity is the initial angular velocity plus the angular acceleration times time. This is the displacement. The final displacement is equal to its initial. Final position is initial plus the initial angular velocity times time plus 1/2 the angular acceleration times time squared. And just put one more. We have the angular acceleration squared is equal to its initial, the angular velocity squared is equal to the initial angular velocity squared plus 2 times angular acceleration times its change in position. Okay. So we're sort of gearing up to be able to do problems that deal with something that's spinning. By now, we should be comfortable using equations that look like this. And by sort of switching to this spinning reference point or way of thinking, we've made our life so much easier instead of having to recalculate position vectors all of the time. So good thing to do if we're given a real world problem would be to say, like, is this thing spinning? Well, let me quickly sort of convert to this angular, finding the angular velocity, the angular acceleration. Then I might be able to convert back to a Cartesian coordinate system later. That's all I have for today. Next up, we will see how to maybe use these in some examples. They're going to end up being very similar to some problems we've seen before. So it should be easy introduction to this material. If you guys have any questions, any concerns, let me know and I'll get back to you. Otherwise, I'll see you guys later.